Hi everyone, my name is Tushar Kumar Jain, and I am delighted to share this video to present our work on the experimental determination of a non-classical Glauber-Sudarshan P function. I am joined by four brilliant group members here: Gaurav Nandi, Soikot Saha, Vasudev Dubey, and Pratham Bhatt, who will each discuss different aspects of this paper. And together, we will walk you through this fascinating research and break down each part to give you a comprehensive understanding. So let's just dive right in. Uh, Let me start by summarizing what this paper is about. In quantum optics, the Glauber-Sudarshan P function is a powerful tool for distinguishing classical from quantum behavior. A state is classical if its P function can be interpreted as a classical probability density. But sometimes it takes negative values, and then we say that the state is non-classical. But here is the challenge. The P function is often highly singular, making it very difficult for us to measure it directly. So in this work, we tackled this problem by reconstructing a well-behaved but still non-classical P function for a special type of quantum state, which we call single photon-added thermal state, SPATs. Using parametric amplification of a pseudo-thermal source and balanced homodyne detection, we experimentally sampled the state's characteristic function and then applied a Hankel transform on this characteristic function to reconstruct our P function. And the key result, we observed that statistically significant negativities are there in the P function, which we can directly visualize as its non-classical nature. And this is not just technical achievement, it's a foundational validation of quantumness as originally discovered or originally defined by Glauber and Sudarshan. It also shows that P function based non-classicality detection is robust even in the face of experimental imperfections and thermal noise. Now, you might ask, why study this? What makes the P function so important? So let me break down into four key motivations. First is the exploring boundary between classical and quantum. One of the deepest questions in physics has always been understanding where classical descriptions fail and where quantum behavior takes over. So this P function gives me a sharp criterion. If it is negative or singular, the state is non-classical. By studying states like SPATs, we probe this fine boundary directly, revealing how quantum mechanics departs from classical intuition. The second is characterizing non-classical features. So non-classicality isn't just a binary label. It comes in many forms: tweezing, entanglement, or negativity in quasi-probability distributions like the Wigner or P functions. The P function is especially telling because its negativity rules out any classical interpretation. By reconstructing it, we get a clear, unambiguous nature of quantum behavior. Third motivation is the practical reconstruction of the P function. In theory, P function is a powerful tool, but in practice, it's often too singular to measure. But however, these pairs are special. Why? Because their P functions are smoother, which make experimental reconstruction feasible. And this opens doors for many studies of quantum states in real world settings where imperfections exist, but we can't hide them under the underlying physics. The fourth motivation can be bridging theory and experiment. So finally, this work is about closing the loop between theory and experiment. Quantum optics, as we see in our class and Anshuman Sir's lab, has long predicted the non-classicality of states like SPATs, but without experimental validation, these predictions remain abstract. By reconstructing the P function, we bring theory to life, showing that quantum features aren't just mathematical curiosities, they are measurable, tangible phenomena. So let's begin with most beautiful demonstration of quantum mechanics, Young's double slit experiment. Here, light shows us its dual personality. It creates interference patterns like a wave, yet delivers energy in discrete packets like particle. And lasers, for instance, exploit light's wave-like coherence, while quantum cryptography uses its particle-like properties through photon entanglement. So Understanding this duality of light helps us push boundaries in photonics, leading to breakthroughs from ultra precise sensors to the uh, modern quantum computers of tomorrow. Now, before we dive into quantum behavior, let's recall how classical physics describes light. Here, light is a continuous electromagnetic wave, completely characterized by its amplitude and phase. The intensity we measure is simply proportional to the square of the electric field amplitude. But this description explains wave phenomena like interference and diffraction. But we see it's incomplete when we look closer at the quantum world. Quantum mechanics revolutionizes our understanding by introducing the term photon, the smallest quantum of light. Quantum electrodynamics describes light as quantized excitations of the electromagnetic field. And this quantum description reveals behaviors that have no classical counterpart. So we can categorize quantum states of light into three fundamental types. Uh, First will be coherent states, the states which are mostly like classical waves and are what we get from an ideal laser. Second is thermal states. This describes light in thermal equilibrium, like what comes from a hot filament. And third is single photon states, also called Fock states. These represent the most quantum behavior. Uh, I'll say this is the light that comes in exact photon number states. What is the key difference? Classical states can always be described by well-behaved probability distributions, while quantum states often require more exotic descriptions, which brings us to our main topic, the Glauber-Sudarshan P function. With this theoretical foundation which I have laid, I'll now hand over to Mr. Gaurav Nandi, who will explain coherent states in detail as well as their P function representation. Gaurav, it's to you.
Uh, Thank you, Tushar, for the great introduction to this paper. Let's start with introduction to the coherent state. So the coherent state was first introduced by Roy Glauber in 1963, for which he had earned Nobel Prize. What makes them special? They are the quantum states that are most closely resemble classical light. Mathematically, a coherent state, alpha, is defined as the eigenstate of annihilation operator A cap. So as we can see that A cap alpha is equal to alpha at alpha state. So this alpha is a complex number which encodes both amplitude and phase information. We can expand on this state in terms of the photon number states. As we can see in the next line, that alpha is equals to e to the power alpha square, mod alpha square by 2, summation over all the photon states. The Glauber-Sudarshan P function gives us a powerful way to express any quantum state rho in terms of coherent states. So rho cap, which is the density matrix, is equals to integration of P alpha P alpha and an operator like liver part. एक बार pause करें, एक बार ये वाला so rho cap is equals to integration of P alpha alpha d square alpha. So here P alpha plays the analogous role to classical phase space probability distribution. Now I would like to highlight important properties of the P function, and I will derive it on the board. I will show that the P function integrates to unity just like a proper probability distribution should. This comes from the requiring that trace of rho is equals to 1. So let me just derive it. So trace of row cap, we'll just replace the row cap which we have got. This is the square of the summation. P of alpha, T square alpha is equals to 1. So this shows that the P function integrates to infinity unity as expected. Uh, uh, Now we'll derive for a pure coherent state gamma. The P function should give us a Dirac delta square alpha minus gamma because coherent state is a state in which the uncertainty is the least and therefore they correspond to a precise point in phase space. So let me show you the derivation. So beta, let beta be any coherent state. Yeah. Now we take an inner product with the row. We know that beta alpha inner product gives us the e to the power minus half beta square, e to the power minus half beta square. So taking the e to the power minus beta square out. Now, let us consider a pure state, like pure state, pure coherent state gamma, where rho is equals to gamma, yeah, outer products of gammas. So from this, we will get that And from previously P alpha, which we know that e to the power alpha square. So first minus. So, but the integral is just a two-dimensional form of the this part is just a two-dimensional Dirac delta function. So we can say that P of alpha is equals to delta square alpha minus gamma. So, however, this is a crucial point for some quantum states as P of alpha behaves in ways that would be impossible for classical probabilities. Uh, say when we calculate the expectation values of normally ordered operators, we get something that looks uh, looks deceptively classical. Say the average of an operator is equals to trace of rho cap or rho cap into uh, that operator. So if P alpha was always positive and well behaved, we can interpret this exactly like a classical average. But when there are negatives, P alpha behaves has some negative regions, or P alpha behaves like a singular. There is no classical counterpart to it. Let's uh, see an example which involves P of alpha being going to singularity. Uh, let's uh, so let's examine one of the clearest examples of quantum behavior, the single photon state, which makes the state special in its P function. The P function which we get from the state 1 is equals to 1 plus del del alpha into del del alpha star delta alpha. This looks complicated, but let me break down what it means. The delta function uh, represents the vacuum state, while the derivative terms account for the single quantum excitation that makes it a photon state. I am going to walk you through how we arrive at this expression. Uh, the key insight here is that the derivatives are what makes the P function singular. They are the mathematical signature of states quantum nature. Let me derive it for you. Hmm. So, we know that one state, outer product of one state is equals to a dagger 0. Delta alpha and alpha. So from here, we know that a dagger alpha is equals to alpha star plus del del of alpha, and from this we can get easily that AK is equals to t square delta alpha star. After a few simplification, we'll get that. We'll get that one. Two p square alpha 1 plus del del star. So by comparison with the definition, the p function will be 1 plus del of alpha into uh, del alpha star. So this distinction isn't just mathematical, it's crucial for the quantum technologies. Non-classical light enables application like quantum cryptography, where single photon states provide security against eavesdropping. The P representation gives us powerful tool to quantify this non-classicality through its departure from classical probability distribution. With that, I will hand it over to our previous speaker, Mr. Tushar Kumar Jain, who will introduce us to single photon added states called SPATs. Thank you.
So we have seen how single photon states have highly similar P functions, as Gaurav explained. But this creates a practical problem. In the lab, experimental noise and finite resolutions make it nearly impossible to directly measure these sharp and singular features. This is where single photon added thermal states, SPATs, come to our rescue. They give us a way to study non-classically with well-behaved P functions that still show clear quantum signatures. Let me outline what we will derive for SPATs on board. Uh, we'll first start with thermal state rho th with mean photon number n bar, and then by adding a photon in it, we create our SPATs P, or say rho. Uh, After normalization, we'll obtain the final beautifully simple form, which is shown here on the screen. So I'll derive it now. So for single photon state, the density function behaves as rho proportional to a dagger e to the power minus beta a dagger a a, where this beta is always greater than 0 and this m is integer. Now, what happens is that we can write this in context of thermal states. So this will become rho proportional to integration of e to the power minus alpha square by n bar a dagger e to the power minus beta a dagger a, and here a dagger. Now, if I here since we are writing this for thermal states, instead of this e to the power minus beta a dagger, we'll write this. So what I'll get ultimately is this rho proportional to e to the power minus alpha square by n bar a dagger alpha d2 alpha. Now, if I act this creation operator on this coherent state, what I obtain a dagger alpha e to the power minus alpha square by 2. So I've explained this in my project report on in Jupyter notebook. I am just taking the final derivation, which final result which I get after deriving all of this. I get in form of derivative of alpha, the coherent state multiplied by mod of alpha square by 2. So this whole derivation is done by me in the Jupyter notebook. Uh, so after uh, substituting this uh, action of creation operator on coherent state, I'll obtain rho proportional to integration of pi n bar, where n bar is the mean numbers, and e to the power minus alpha square del by del alpha star. Alpha star is because there is bra state also there for coherent state. This is why we are getting this alpha star, and e to the power minus alpha square 1 plus 1 by n bar, and now the outer product of alpha multiplied by d2 alpha. So now these derivatives in this equation can be expressed in the terms of Laguerre polynomials. So the final result for P function after normalization and putting Laguerre polynomials in place of these derivatives, we obtain rho proportional to 1 upon pi n bar e to the power minus alpha square by n bar Laguerre polynomial 1 plus 1 y n bar multiplied by alpha square. This is the uh, what we say amplitude or x of the Laguerre polynomial divided by d, where this d is shown in the Jupyter notebook. You can see instead of writing the whole d, I can just writing this as d. Now we can see that Laguerre polynomial uh, oscillates between positive and negative values. So when Laguerre polynomials becomes negative, my p1 alpha, this which I will obtain from this row, clearly becomes negative when my Laguerre polynomial becomes negative. So after simplifying the final expression, I get p1 alpha equals to 1 upon pi n bar cube 1 plus n bar alpha square minus n bar e to the power minus alpha square by n. So this is the final expression of p function for our these spats. Now considering alpha equals to so uh, I'll just share my Jupyter notebook. Mhm. So now if I consider alpha equals to x plus iota y, I will get alpha square equals to x square plus y square. Now if I plot a 3D plot p alpha, I'll get this 3D surface for p alpha versus real part of alpha and imaginary part of alpha. So this is theoretical reproduction of the 3D plot given in the original paper, which was done using experimental data there in the paper. Now, if I take a cross section of this 3D P function along a radial line, I will get the following plot, the next plot. This is the 2D plot of P alpha versus alpha, which I have reproduced, and experimental plot of the same is given in the paper. The key insight here is that while this P function is smooth and well behaved, it still becomes negative, which we can see in this plot, which maintains that crucial quantum character. Now, what makes SPED such a powerful tool for experiment? First, its experimental accessibility.
Recording in progress.
So I think we lost our internet connection. Sorry for that. But I am back now. And I was saying what makes SPAT such a powerful tool for experiments. First, it's experimental accessibility. Unlike the single photon states, SPATs can be generated relatively easy using these parametric amplification of thermal light. Second specialty of SPATs is it gives us well-behaved P function. The P function is smooth and it doesn't involve any derivatives of delta functions. The third is clear non-classical signature. So the combination of properties makes SPATs ideal for testing fundamental quantum features while working within the practical experimental constraints, which we were not able to do in case of the single photon states. So what's the big picture here we can see is that the SPATs P function beautifully illustrates a deep principle. Quantumness isn't about mathematical singularities, but it's about the impossibility of classical interpretation. Even with a smooth distribution, the negative values tells us that we are seeing genuine quantum behavior. This is exactly what we have demonstrated in our experiment. And uh, Vasudev Dubey will now show you how we actually measure and reconstruct this P function in the lab. And with this theoretical framework in place, I'll now hand over to Mr. Vasudev Dubey, who will walk us through the experimental realization of these ideas. And this is exactly what we have done in our experiment with single photon added thermal states, SPATs, which Vasudev will discuss in detail.
So, hello everyone. So, thanks Tushar and Gaurav for nicely explaining the basic part of the Glauber-Sudarshan P function, the SPATs, coherent states, and non-classicality. Now that we have seen the theoretical framework, let's discuss how we actually create and measure these single photon added thermal states called SPATs in the lab. So, the key challenge is generating quantum states that they are stable enough to measure their non-classical properties. So our experiment relies on the beautiful quantum process called spontaneous parametric down conversion. In short, it's called SPDC. So let me tell you how it works. So SPDC is a quantum optical process in which high energy photon from a laser called pump photon interacts with a non-linear crystal. As a result, the pump photon is split into two lower energy photons that conserve the total energy and momentum of original photon. So these two emerging photons are emitted into two separate spatial or spectral modes, commonly known as the signal and the idler modes. So the goal of this experiment is to generate a SPETS and analyze its quadrature properties via homodyne detection. I will tell you what is homodyne detection later. So SPETS is created by combining classical thermal light with single photon source, resulting in quantum state with non-classical characteristics. So let me share my screen first. Okay. So everyone can see my screen. Okay. So first is the laser source. So we start with a titanium sapphire laser producing ultra short pulses with around 800 nanometer. So this laser serves two purposes. First, it acts as pump beam to drive the parametric amplifier, and the second one is that it is used as a local oscillator for homodyne detection. Now, this laser beam is incident on an LBO crystal, LBO, the lithium borate crystal. So this is a non-linear crystal which converts the fundamental wavelength into its second harmonic. And why we want this conversion? So this second harmonic beam is essential as it provides the required energy for PDC, the photometric down conversion, parametric down conversion, sorry. And this 400 nanometer light is directed onto the video crystal, the barium borate crystal, where PDC process occurs. This generates the signal in the idler photon pairs. So to create thermal state, as we want to create the SPATs, the single photon added thermal states. So to create the thermal state, we the scatter part of the laser beam, this uh, is directed using the HT and HR. So HT and HR are transmittive and highly reflective things. So after directing this onto this mirror, we use the rotating disk, which randomizes the phase and amplitude of the light, simulating a thermal light source. The resulting speckle pattern gives us the random phases and amplitude beam. So this thermal light is then seeded into the parametric amplifier for the next stage. So the real magic happens in the BBO crystal, where the SPDC occurs. The thermal light is combined with the pumping beam and pass through the BBO crystal. This setup emits two photons of equal energy. The first one is signal and the second one is idler. The single photon is detected using a single photon counting module, shortly known as SPCM, which is placed in the idler beam path. When our idler detector clicks, we know a photon pair has been created. This is known as a heralding of single photons with the thermal light beam. Between SPCM and BBO, there is a filter which is placed to pass the correct wavelength photons and to reduce noise. Now, at last, the homodyne detection happens. We measure the quadratures using balanced homodyne detection. A beam splitter is used to interfere the heralded single photon with the thermal light beam. The output modes are directed towards two photodetectors. One is this and another is this, where the currents from both the detectors are subtracted to obtain different quadrature values. For each laser pulse, the homodyne detector records a quadrature value. Many quadrature measurements are taken at random phase settings of this local oscillator. Since the state is assumed to be independent of its phase, the local oscillator's phase, the reconstruction of P function simplifies to the radial symmetry in phase space. After that, a Henkel transform is then applied to extract the final P function. Okay. So with this carefully designed setup, we are now ready to see some quantum magic. I'll hand over to Mr. Sarkat Saha, who will show you how we have reconstructed this P function with their beautiful negative regions using characteristic functions of SPATs. So over to you, sir.
Yeah. Hello, everyone. I am Shoiba. I will now start describing about the characteristic functions which are being obtained experimentally. So, to fully characterize our space, we need to examine like its phase space properties through the characteristic function. This function, denoted as phi of beta, gives us a complete description of the quantum state in phase space. The characteristics function is defined using the displacement operator d of beta, where the phi of beta is related to d of beta, like this equation, which gives phi of beta is a trace of rho of d of beta, where d of beta is the exponential of beta alpha dagger minus beta star alpha, which shifts the states in phase space. So I will show you the derivation for obtaining this characteristic function of Siemens. Yeah, so let's start with the phi of beta, which is given by this trace of rho d of beta. Now, since d of beta is exponential of beta alpha a dagger minus beta star a dagger, and since rho, which is the thermal density of matrix, so this is given by 1 by n plus 1 summation n bar plus 1 n. So, and the outer product of n, where n is the number state and n bar is the average number of photons. So, where n bar given by the Bose-Einstein condensate as e to the power h bar omega by kBT minus 1. So, afterwards, rho spats which is uh, which is obtained by creating a single photon in the thermal environment is obtained as a dagger of low th a dagger by trace of a dagger rho th of a. Then after obtaining this rho th, we'll get this as summation pn nn, where the pn is the probability defined by the initial factor, like the 1 by n bar plus 1 summation in n bar plus 1. So after doing this simplification, the results are as follows. This trace of a dagger rho th a is given by summation n n n plus 1, and since this rho spats was given by the previous expression. So after using these derivations, I will get the row spats as 1 by n plus 1 summation n pn n plus 1 n plus 1 times n plus 1. Now phi of spats, which was given as trace of rho times d of d operator. So after using this expression of row spats, we will get the phi spats the as the expression like 1 by n plus 1, uh, then pn n plus 1 n plus 1 times dv n plus 1. So using the known rule of m as e to the power minus half mod beta square lm of mod beta square, which is where lm is the mth order Laguerre polynomial, will finally obtain the phi of spats as the final expression, where 1 minus 1 plus n bar uh, beta square times e minus n beta square. So the more steps are given in our Jupyter notebook. And now I'll move forward with the reconstruction of the p function obtained from this characteristic function. So now that we have the characteristic function, how do we say we would find the p function? The key is recognizing this Fourier transform relationship. So the by Fourier transform, the phi of beta is related to this p of beta alpha as the Fourier transform of each another. And And then this and since in the 2D radial symmetry problem, the Hankel transform is obtained to the Hankel transform is obtained from the to get this P of alpha. So we'll relate phi of beta to P of alpha as the Bessel function, and this transformation would result in. Let me share my Jupyter notebook where I will explain this. Uh, explain these relations clearly. Yeah, so this is the phi of beta which we obtain from our law, and it is related to this by this equation, and then after performing this Fourier transform and all, we'll finally get the expression of phi of beta in terms of p of phi of beta in terms of p of alpha, and then p of alpha would be similar the inverse Fourier transform of phi of beta. Now in the radial case of 2D systems, the it reduces the Hankel transform, where the Hankel transform is given by this relation, and the and this relation, and since after obtaining phi beta from our experimental determination of quadratures, we will find the P of alpha. So now with this powerful mathematical tools in hand, the characteristic function description and Hankel transform reconstruction, we are now ready to see the experimental results. So I'll hand over to our another group member, Mr. Pratham Bhatt, who will derive the error in characteristic function and show how all these pieces come together in our actual measurements of non-quantum non-classical. तुम मुझे सब कर दे तुम इधर बैठ सकते थे इसको मैं एक साथ मैं इधर एक फ्यूचर फ्यूचर करते हैं We have 8 minutes left. 8 minutes. I won't discuss the future prospect. So you take all these 8 9 minutes.
4 minutes. 4 minutes are remaining. Hello, I'm Pratham, and I'll explain the derivation of the error in the characteristic function. So, this is the estimate of the characteristic function that we calculate from the experiments that you measure. So, once you do that, you have the estimated uh, characteristic function. Now, for any quantity, the variance is defined by this formula where E is the expectation value. Suppose phi beta is y, variance of y is expectation of y square minus expectation of y whole square. So let's calculate the first and second terms in this formula. So first, let's calculate the expectation of phi of beta. So we take equation 48 here and just apply the expectation to both sides. So once you do that, the RHS just becomes this. Next, we use the linearity property of the expectation. Uh, yeah, using this factor times the sum of the expectation of the individual terms in this expression. Uh, Now, what is the expectation value of e power I beta xj? If we assume xj's to be independent and identically distributed, each of the expectation value of each of these xj's will be just phi of beta times expectation value of phi of beta times e power minus beta square by 2. And since each of term is this quantity and there are n of these terms, it is just n times e power minus beta square phi of beta. So we just substitute that here. uh, yeah, we just substitute that here, and we divide by n. Yeah, we substitute that for that gives us the result that expectation of phi of beta is phi bar of beta. Okay, now let us calculate the second term, expectation of phi of beta square. So we'll just write the summation. We'll just write it in terms of summation, and we'll just combine that into two types of terms when j equal to k and j not equal to k. When j equal to k, you get e power I e power I to the power 0, which is just 1. And when j not equal to k, we get this kind of term, e power yeah, we get this kind of term, e power xj minus xk. If e power mod beta times xj minus xk, uh, it can be shown that this is just phi prime beta whole square. I mean, yeah, phi bar of beta whole square. Uh, if we uh, if we combine both these terms, we get the result that expectation value of phi bar beta whole square is this quantity that is shown here. Finally, we will combine both these that we started, which was here. We just substitute this, and we get the result that your error in the characteristic function uh, is this quantity shown here. So yeah, this is the error in characteristic function. Yeah, I'll now explain the results of the paper that are explained in the paper. So first, we measure the yeah, from the measured quadrature values, we calculate the uh, yeah, from the measured quadrature values, we calculate the characteristic function shown previously. Uh, This is the symmetrically ordered characteristic function. Now, to get the P function, we need the normally ordered characteristic function, which for the case where it's phase insensitive, it is related to quadrature by related to the quadrature characteristic function as shown here. Uh, yeah. Now, the plot that is shown. In the plot, you can see the characteristic function that is calculated and that we get from the experiment. Yeah. So here there are two curves A and B. A corresponds to a spat with n bar equals 1.1 and B to a mixture with 19% thermal background and the rest spat with n bar equals 3.71. And this spread that you see, that is the error in the characteristic function that I calculated in the previous part. So yeah, this is regarding the uh, characteristic function. Now next we need to get the P function. So to get the P function, it is related to the characteristic function by this formula that is shown here. Because there's radial symmetry, the two-dimensional Fourier transform reduces to the Hankel transform. That is what's shown here. Uh, in practice, we don't integrate this to infinity. We integrate it up to a cutoff beta c, because after this, the contribution of phi of beta becomes negligible, and because of this, we get a stable reconstruction. So the P function that we derive from the characteristic function in this manner is shown in this figure that you can see here. And since the measure states are independent of phase, the reconstructed P representation is also phase independent, and it can clearly be seen that the P function attains negative values, so it fails to have properties of a classical probability density. And this is a direct proof of the non-classicality of the experimentally realized spats based on the original definition of non-classicity. So, next, we will look at a cross section of this curve that I have shown previously. Uh, so that is shown in the next plot, if you see. So here, two curves A and B. These correspond to the two curves in the original characteristic function that I showed in the first plot. So for curve A, the lowest value of the P function is 5 standard deviations below zero. This is statistically significant negativity of the P function, and therefore it cannot be interpreted as a classical probability density. This provides clear evidence of non-classicity as per the definition of the P function. For the P function in B, the lowest value is 1 standard deviation below zero. In this case, we don't observe the non-classicity as clearly as the first case, but it can still be seen. Uh, yeah, at, at this stage, I will conclude the result section. Okay, that's it.